Hi everyone, welcome to your second to last lesson in science for the year. This lesson is on work. Before we get started, I want to do a little warm-up. Ignore the date of this warm-up. It is on potential and kinetic energy. Put the following in order from most potential energy to least. So, assuming this is a roller coaster, the point with the most kinetic energy, or potential energy rather, is point B, and that is because it has the highest, it has the most height. So if you look at B in comparison to D and E, the roller coaster could not get uphill E or uphill D if it had not been high enough, as high as hill B. So it starts off at A and then it goes uphill B. That's where it has the most potential energy. Remember, potential energy is the amount of energy that an object has because of its height above the ground. So because it's the highest height above the ground, it has the most potential to fall the most. And by fall the most, in terms of a roller coaster, I mean travel the fastest down the hill. Point C would have the most kinetic energy. That's where it would be moving the fastest. So, getting into the lesson on work and power. What happens when a rocket is launched into space? Well, when the rocket's engines are fired, chemical energy in the fuel is transferred to kinetic energy in the rocket. That transfer of energy is called work. Sorry, I went too fast. So, in a physics class, you'll be using this work equation, the work equation I'll give you in just a second, and the units. And the first unit you'll use is joules. This means that the units of work are the same as units for energy, and they are both measured in joules. Just like we measure time in seconds or minutes or hours, we measure joules, or work and energy, in joules. Okay, so what factors affect work done? The amount of work done is affected by several different things. So if you look at these two different weightlifters, the one on the left is sweating. The one on the right looks like he just went over and he picked the weight up, lifted it above his head, and it's all easy. But really, the weightlifter on the right is doing more work because he's lifting a heavier weight. So the amount of work done depends on the size of the force that moves an object. And the guy on the right is exerting a heavier or a bigger force than the guy on the left. So that guy's doing more work. Work is also affected by another factor. And if you look at these two firemen, you notice that one's higher above the ground than the other. Well, the fireman on the left is doing the most work because he's climbing higher. So the amount of work done also depends on the distance that an object moves. And put that together. Does the application of a force to an object always result in work? This guy is working really, really hard, it looks like, but is he actually doing work? He's pulling, but is that box moving? It is not, and so therefore no work is done. Just because he's pulling hard does not mean that work is done, because that thing isn't actually moving. So work done on an object can be calculated using the equation force times distance. If either force or distance is 0, well, guess what? Anything times 0 is what? 0. So that would mean 0 work is done. Okay? So hang with me here. Again, you're not going to have to actually calculate this until a physical science or a physics class, but you do have to understand it. And so seeing the equation can really help you understand it. Force is measured in newtons. Distance is measured in meters, and work is measured in joules. Again, you don't need to know those units right now, but they're helpful to help you understand it. So if a question asks you, or if you're asked to explain whether work is done or not, you just guessing yes or no is silly because it's easy. If a force isn't applied, so if you're just sitting there looking at a cup sitting on the table, you're not putting a force on the cup, and if the cup is just sitting on the table, is it moving? It's not moving. The cup has lots of other forces even though you're not touching it. There's gravity, there's the force of the table pushing up on the cup. However, the cup isn't moving. So whatever the force is times 0, because it's not moving, would equal 0 work done. And let's say you pick a cup up and you walk it to the kitchen. You are applying a force on the cup and you are moving at a distance. So you will have numbers other than 0. So the only time you'll get no work done is if you don't move anything, if nothing moves, or if there's no force. And more often than not, it's nothing moves, because there's always different forces being. All right, so power is the rate at which work is done. A more powerful engine, therefore, does work faster, or transfers energy faster than a less powerful engine. Both of these planes are about the same mass. However, the jet engine has more powerful engines. Or the jet has more powerful engines, and that's because the energy in the fuel is transferred to kinetic energy faster, so it has a greater acceleration and a higher top speed. So that means it speeds up much faster. Power is calculated by the amount of work done in the time it takes to do that work. So if a machine can get work done in a quicker amount of time compared to a different machine, it's going to be a more powerful machine. And companies want to have more powerful machines because that equals more money for them in a faster amount of time, more likely than not. Again, these are the units: joules for work, seconds for time, and watts for power. And something that you might be familiar with that has the measurement of watts is a light bulb. And so that measurement actually comes from this equation, the work done, and now we're talking about electricity. So how fast does it take for electricity to be transferred, and in what amount of time? And that gives you the measurement of the light bulb for watts. And you know, different watt light bulbs are different levels of brightness. There's a really cool song. I can't play it from this presentation. However, it is the video posted right underneath this video, and it's Mr. Edmonds singing Work and Power. He is one of my favorite science singers. He's actually a science teacher who makes up all these really cool science songs. I've used him for years. He's cheesy, but he really helps you to remember. His songs get stuck in your head. So if you have a hard time understanding Work and Power, go listen to his song a couple times, and it's really, really helpful stuff. So the next activity that you guys are going to do is called acting out work, and you'll actually get to see examples of when work is done and when work isn't done, and you're going to do it. So keep these notes with you and take this information and apply it to something real. Have fun, and have a great productive week, and we'll see you next week. Bye.